Hello everyone, let's continue. So in the previous videos we came up with some ID/VD curves, and for the NMOS we had done some spice simulations in a couple of videos back. For the PMOS we didn't do any spice simulations, but it was pretty obvious from the values of the voltages that you have. Okay, so PMOS is just an inversion of NMOS, and the direction of the current and everything, those were all related over here, those are all mentioned over here. So just observe this PMOS and NMOS or the CMOS inverter for some time. So now we have tons of voltages over here. We have VGSN, we have VGSP, we have VDSP, we have VDSN, and so on. But when you try to look into the inverter from a logic block point of view, you will be having only two voltage values. You will be having V in and you will be having V out. That's all you will be having, and the internal node voltages will not be even visible to you guys. Okay, so there should be some way to identify the voltage and the current curves in such a fashion that they are just a function of only two voltages, V out and V in. In that way we can relate what is the value of V in, and at that value of V in what is the value of V out, and that's all we need to identify to get the load to get the voltage transfer characteristics of the CMOS inverter, which will eventually help us to calculate the delay. Because whenever your input sweeps, or whenever input voltage goes from 0 to 1, the output voltage goes from logic 1 to logic 0, and the time between which it goes from logic 1 to logic 0 on the application of 0 to 1, that will be the delay of your cell. But the important part is all of them are a function of V in and V out only. There is no VDSP or VGSP and so on in the logical cell. If you look into an inverter, if you look into any gates, there are inputs and there are outputs. The internal node voltages are not even visible to a user. Okay, because those are not being used anywhere in your digital design. So let's try to get rid of the VGS and VDSP and all the voltages that we have, and try to come up with some way to make this as a function of only V in and V out. The current is still understandable, but we'll take only one current. We'll take either IDSN or IDSP. Most preferably we'll take IDSN, the drain current of the NMOS, and we'll have only one value of current. So what we'll do, we'll play around this equations, we'll play around this equation and these curves, and try to identify some way to modify or to model these curves as a function of V in and V out only. Okay, so let's try to do that. And the reason for that is because in a real world, in a real digital design, you don't see the internal node voltages. All you care about is the V in voltage and the V out voltage. Okay, so let's try to identify or convert these curves in a fashion that they are only a function of V in and V out. Okay, so we'll push this somewhere else. We'll keep this at the right hand side, and I will tell you the exact steps to obtain the voltage transfer characteristics. So when we say voltage transfer characteristics, we will be obtaining some curves which are only a function of V in and V out of a cell. Okay, so let's do that for a static CMOS inverter. Okay, so the first step, let's look into the first step. We'll take the we'll draw a table over here. Okay, in one column we'll put VGSP, we'll put all possible values of VGSP. For example, over here VGSP is 0, so we'll put 0 over here, and we have 5 different values of VGSP, so we'll take 5 different values of VGSP over here. Okay, that is the first thing. Second thing, that we will assume that it's a long channel device, and that's why we have kept a VDD of 2 volts. This is applicable, the steps that I will be explaining, that is applicable for CMOS inverter of any node. Okay, but for now let's assume that it's a very high node, it's a very large node, and we have a VDD of 2 volts, and we'll be using this VDD value for our calculations. Once we move to lower nodes, we'll be looking into what happens when you lower your VDD values and so on. So most of the calculations or most of the explanations remain same when you even lower down your voltage. Okay, so let's try to use VDD, or let's assume a value of VDD as 2 volts. So with some we had deduced some observations over here. So let's try to first convert VGSP as a function of V in. So over here, if you see this equation, VGSP was V in minus VDD. We explained how do we get this in the previous videos. You might want to have a look into that. So in this case, when you see V in, if you just try to evaluate V in is VGSP plus VDD. That's what we have mentioned over here. V in will be VGSP plus VDD. So the reason what we are doing is we are trying to convert VGSP as a function of V in only. We'll try to convert all the voltages as a function of V in and V out. So this is the first part to it. So we have Vin as VGSP plus VDD. So let's write down all the values over here for the respective VGSP. So for example, in this case, your VGSP is 0 volts. Okay, so VGSP plus VDD is 0 plus 2, it becomes 2 volts over here. In this case, VGSP is negative 1.5. Okay, so V in will become negative 1.5 plus 2, which is equal to 0.5, and so on. So this is the way we fill up this particular table. Okay, that's the first step to get this. Okay, next is we have this particular voltage levels, we have this particular V in values, and by observation we have seen that your drain current of the PMOS has got an exactly opposite direction than that of NMOS. So we have this equation. Remember, we mentioned some time back we'll put everything as a function of only single current, either IDSN or IDSP. In this case, since we are already familiar with the functioning of IDSN, so let's try to convert everything into IDSN as well. Okay, so this IDSP, it will just shift axis over here. So if this was negative IDSP, your positive IDSN will lie somewhere over here. And it makes sense because your IDSP is negative of IDSN or vice versa. So we have this drain current, or we have this current values, we have this voltage values. Let's try to shift this particular curve. Let's try to move this particular curve as a function of IDSN and Vn. So basically what we have to do at every value of VGSP, for example over here VGSP will plot a value of Vn which is 2 volts. Okay, for VGSP2, which was negative 0.5 volts, will plot something in this curve which is of 1.5 volts. Okay, so let's see how does the curve look like. This is how it looks like. So for example, in this case, any value which is VGS negative VGSP, which is negative 2 volts, for that, if you see a drain current of IDSP somewhere over here, for the same value of negative VGSP and for the same drain current, this is how your curves looks like. So basically when you say negative VGSP, it essentially means your input voltage is 0. Your input voltage is 0, and your IDSP, your negative IDSP is a positive IDSN. So your negative IDSP has been just shifted to positive IDSN. So we are representing this curve into very handful of voltages. So by this shift we have got rid of the VGSP. Let's look into this particular curve even more detail. Let's go one by one. So negative VGSP, when it was 0, when negative VGSP was 0, your Vin is 2 volts, your Vin is 2 volts. Okay, and whenever your negative VGSP is 0, is your drain current is 0. So over here also you see your drain current is 0, whether it's negative or positive, it's 0. Next, when we move to negative VGSP2, which is this particular curve. Okay, negative VGSP2 is negative 0.5, which is plus 1.5 volts, which is Vin equal to plus 1.5 volts. And for Vin equal to plus 1.5 volts or negative VGSP of negative 0.5 volts, you see a drain current which lies at this point somewhere. Okay, and similarly the inverse of it, basically in the terms of IDSN, the same drain current will lie somewhere over here. So for Vin equal to negative 1.5, your IDSN will be at this value. And this curve is equivalent to this curve because of the calculations that we just did. It's just a hypothetical calculation that we are doing. This all exists in real. We are just this is the one that exists in real. We are converting these voltages into a format in which we can identify the delay values, or we can plot the load voltage transfer characteristics. We are converting everything as a function of V in and V out, and this is the first step to it. Okay, let's look into the third curve. For example, VGSP3, your negative VGSP3 was negative 1 volts. That meant your Vin was 1 volts, your Vin is 1 volts, and exactly the same value of IDSP is maintained at IDSN. So your negative IDSP becomes your positive IDSN. Okay, so and so on. You will have VGSP4 as negative 1.5 to which get converts to 0.5. So same thing we have mentioned over here. For the same curve, we have we have Vin equal to plus 0.5 volts, which essentially represents your VGSP as negative 1.5 volts, and the drain current for VGSP4 is being retained over here but in a different direction, and it all remains the same. Okay, so what we'll do, we'll try to deep dive more into this curve, and we have to obtain the next set of curves, because till now we still have VDSP present over here. We need to get rid of VDSP. That is first. We need to take the NMOS ID VDS curves and convert VGS and everything into a function of V in and V out. So let's try to do all this in the next video. Thank you.